So I'm going to talk as a outsider on this computer science thing. But we have been using the neural network, the recent development, and we are also working with Ulysses and others on applying neural network to physical problems. And so in that regard, we are the users. We try to handle our very tough problems with neural network. So I'm going to show you a few examples here, and it's just see how what kind of physics that I am interested. We want to deal with that very complicated problem with neural network. So this is we have been working. This is actually a team, and I'm also actively using the HPRC facilities that Lisa just mentioned. We are running big programs, searching for supernova using very telescopes that can cover almost the whole sky in a few days. Okay, so I will start with something a little bit boring, but that's really the toughest problem, I think. One of the toughest problems in astrophysics. That is relative transfer. And we see the sun. The sun produces light, and the sunlight reaches us. But it actually takes a long time for a photon to go from deep inside the sun to its surface, and then it takes 8 minutes to come here after it emerges from its surface. And during that process, sometimes some photons can travel millions of years, actually trapped in the sun. Okay, how does that photon come out from deep inside sun to us? You see, all the information is lost. Now, when we observe the sun, we cannot see deep into the sun. We cannot see directly because of all these multiple scattering, all these interactions of photons with the material, stellar material. But the solar spectrum is nonetheless the simplest spectrum we can imagine in astrophysics. Okay, that is because the sun is more or less stationary. It doesn't expand wildly. It doesn't contract. Therefore, all the features are actually very narrow and well resolved. You can see each of these narrow features there, showing those dips. They are mostly, they may be blends, but most of those features are actually produced by a single atomic transition. So therefore, you can point to that line and say, okay, this is a line from hydrogen. That's a line from helium. Okay, therefore, you can also measure those lines and say, okay, now I measure the hydrogen, I measure the helium. Okay, that makes sense. Very, very simple. You can just measure this feature and see how strong they are, and then convert that into some kind of astrophysical quantity, based, of course, on certain astrophysical models. So you can easily extract the spectral features. You can build models for the observations. Okay. And sometimes you can make it more complicated because the lines may be polarized. In that case, the photon, you also try to measure the spin, spin of the photons, or it's equivalently, it can also be the direction of the electric field that the light oscillates. So you can make things complicated, but you can really make things very complicated now if you take into account all the atomic transitions that's happening in the sun. And now it's not simple anymore, because in addition to these very, very strong lines, there are millions, hundreds of millions of weak lines. And sometimes you are interested in those weak lines. So now what are you going to do? So that's the challenge. But neural network is the the tool that actually is designed to handle this kind of massive amount of data or models. Okay, here are some examples. You can see on the left over there, you can see that that's typical stellar spectrum. They're not identical. Not all the suns are like all the stars are like the sun, but they some stars are more compact and more massive, or some are more diffuse. The large in size, but probably also well, when they are large, the stars are probably cool. I mean, lower temperature, higher temperature. The density profiles may be different. They may blow stellar winds. So those make things very complicated. But for stellar spectrum, you can say people can build pretty good models. Okay. This model, that's comparing model and observations. You can see, the models in general agree very well for some of this data or some of the features. But now there is another challenge here shown on the right. That's what I am particularly interested in. That's the spectroscopic studies of supernova explosion. So a supernova is the last stage of the stellar evolution. Star actually died as supernova. So here you can see this is a sequence of supernova spectra. Now you see it's very different from stellar spectra. That it's very hard to say which feature is due to which atomic species, because the supernova is expanding so fast, and all the lines are blending. You have the lines interact with each other. The line just the one transition from one atomic from one atomic level, the west side of atomic levels will immediately interact with some other atomic species. Everything is now joined, stirred up into a big mess. So now how can you analyze this? How can you now say, okay, I want to know how much gold is being produced in this supernova explosion? Okay? Gold actually comes from supernova explosion. How much iron is produced there? Now, this is not trivial at all. So the state of art for modeling supernova spectra is much, much worse than stellar spectra. Okay, so the challenges are there are millions of atomic transitions for this kind of problem, and the lines can be blended, and sometimes it's impossible to separate them individually. And furthermore, even worse, make it even worse is that the data can be noisy and incomplete. Sometimes you only observe part of the wavelengths, or almost all the time. You only cover part of the wavelength range, but you want to know more. So, and the models are very hard to calculate. I didn't say how hard it is actually to calculate that those models for stellar radiative transfer. It is very, very hard. It takes a long time to calculate a correct model. But nowadays, people invented new ways because of neural network. Okay, it can be done very fast, but it can take days or months to calculate the spectrum. So that kind of success is migrating, spreading over to supernova research as well, but only at its very, very early stage. So we have been working on this, actually trying to model supernova spectra with neural network, with all this, latest development. that can handle this massive amount of data. So here I show that this is actually not a physical model. This is just using neural network to interpolate the data. You can see in this model, the reason I'm showing this, so this is an array of observation. This data are very expensive to take. Take a spectrum on the telescope. This telescope is 8 meters in size, located in Chile, and running this each night costs like hundreds of thousands of dollars or something, crazy amount. And you see, we took this huge array of data. But as a matter of fact, a lot of this information is actually encoded in the data of a single observation. So you can, with neural network, you can actually build a kind of extrapolation or interpolation tools that you just imagine you have one spectrum, then there are a lot of hidden parameters you can train, and then you can extrapolate that information to early and late time. Now you can see the green and the black are comparing the extrapolations and the real observations. They can be very, very close. So there are a lot of redundant information with all these expensive experiments. And with that, we can build physical models. This is not a physical model, but we can indeed build physical models. The physics cannot be correct. The problem is the physics is so hard to calculate. You only get the physics approximately right. And people, you know it's wrong. Okay, yeah, I'm almost done. So now you can extract the essential parameters such as the mass of nickel or the mass of something, the chemical element abundances, those sort of things. So here I show how complicated this is. Okay, so we explode a star. How does a star explode? Somewhere you burn it, like you ignite the burning process, nuclear reaction, and then the stars blow up, and in the end, it creates something really a mess. Okay. So now, with the last minute, I'm going to say something also very interesting, but very, very difficult. This is, we all heard about the James Webb Space Telescope. Yeah. Okay, it's a huge telescope in space, very far away. So this actually makes me interested in doing a crazy object research for something I call cosmic defects or the space-time defects. Okay, what does this mean? Let me just maybe make it brief. So when we observe, take an image of the sky, we think the space is perfect, flat, Euclidean. Okay, we never, for most of us, we never question that. But in astronomy, actually, the space is not Euclidean. If it's Euclidean, it's going to be so boring. But because of Einstein, we know that space-time has structures. So according to the most successful model in cosmology, that the space-time experienced many phase transitions from the point of inflation or Big Bang all the way to today. And this, for phase transition, it's like the temperature drops, the air, the water vapor condensed into water liquid and then into ice. For instance, from liquid to ice, if it goes too fast, it's not going to be a whole complete, block of ice. There will be cracks. There will be pockets of gas trapped in that ice. So that's called defects. So the space-time can have that too, because it expands so fast. So fast that there will be hot blocks of something, the material, early phases of the universe trapped inside our universe. Okay, So it's like the water vapor trapped in ice, something similar. And that usually takes kind of special form. It's not a kind of arbitrary shape. There are physical constraints on that, what that might be. And that creates something, sometime it can, if it's one-dimensional, then it creates a black hole. Well, zero-dimensional. Zero-dimensional defect will create a black hole. And it can also be one-dimensional, then it's a very long string. It can also be two-dimensional, then it's just a flat, surface, and it extends to infinity. Okay, so yeah, so now this thing will break the space-time. The trouble is, so it's like you're holding there's now two beam, a star or a galaxy very far away now will arrive at you with two faces. Okay, with two. Image to you. Okay, so now if you observe a piece of sky, it's like you're going to create, suppose there are these defects of this kind of physical nature, and this is like a simulated image of galaxies, going through these defects to us. And you're going to see a triple image of galaxies over there. And it's really like a broken pieces of the universe. And how can you discover this? This is very hard to discover. But if you discover this, it's certainly going to be on New York Times. Okay, you're going to be famous. But this is something I have been thinking, and I actually coded a little bit, but it's too early for me to say too much about that. This is an image, that I processed. If I lay out the problem, so if you are interested, if you have some cool ideas of how to identify these broken pieces of mirrors, and you're welcome to talk, with me. So, but this is the typical James Webb Space Telescope image. Because in one single exposure, it has like a lot of objects, and what we are searching here is to see if there are little evidence of something broken in space. Okay. All right.